Today we're going to look at the second and final lecture of chapter number 7, and we're still talking about potential energy and energy conservation. Our learning goals for today: the first one, introduce the concept of elastic potential energy; the second, distinguish between conservative and non-conservative forces; the third, solve problems in which both kinds of forces act; and finally, determine properties of a conservative force from its potential energy function. Now, we're going to look at work done by a varying force. In the last lecture, we looked at work done by a constant force, and we looked at the work done by the force of gravity, and we said this is equal to mgy1 minus mgy2, and we defined u as equal to mgy, and we said that the work done by gravity is equal to minus delta u. We assume that the force of gravity is constant near the surface of the earth, and that's what we did in the last lecture. In today's lecture, we're going to take a case when the force is a varying force, and we're going to take a spring, and with a spring you can also either stretch it or compress it, and in both cases you will do work. But we're going to look at the work done by the spring. So if you recall in chapter number 6, when we looked at the work done by a varying force, and we said it's equal to fx dx, and we said it's equal to the integral of kx dx, and we went from x1 to x2, and we looked at the work done applied here on the spring, and we said that this is basically equals to 1/2 kx squared going from x1 to x2, and we said it's 1/2 kx2 squared minus 1/2 kx1 squared. That was the work done on the spring. And we said if you want to look at the work done by the spring, it should be the opposite of that. And that's what we have here. We have the work done by the spring. You can attach a body to the spring, so the spring will do work, and that body, and the work done by it, it's equal to 1/2 kx1 squared minus 1/2 kx2 squared. We have already done that before. Now we're going to define something that we're going to call elastic potential energy, and we're going to say that this is equal to 1/2 kx squared. So if that's the case, then the 1/2 kx1 squared will be u elastic 1, and 1/2 kx2 squared will be elastic 2, and that's again will be equivalent to my saying that it's equal to minus delta u, as we did in the last lecture. So even when the work is done by elastic force, it's equal to minus the change in potential energy, and the elastic potential energy is defined as 1/2 kx squared. Is this point clear? Now, just looking at this elastic potential energy, which is equal to 1/2 kx squared. So if you make a plot of potential on the y-axis, x on the x-axis, so on this side x is negative, which is less than 0, and this side is x positive, which is greater than 0. But in both of these cases, your potential energy is positive, because you have a square here for the elastic, and that's why you have the parabola this way. So regardless of x is, you can choose any point, okay, regardless of x is positive or negative, the value of your elastic potential energy is going to be what? Is going to be positive, and you get this parabolic shape for the 1/2 kx squared here. Now, as we did in the previous slide, we said that the work done by the elastic spring here, it is U elastic 1 minus U elastic 2, which is equal to minus delta U. You know that delta U should equal to U2 minus U1. But what you have here is U1 minus U2, and that's why we have here minus delta U. And S here means spring, and we say that in this case the spring is a conservative force which will conserve energy for us. So like what he did in the last lecture, let's say we have a spring doing the work. We don't have friction, we don't have any non-conservative forces. So you know that in chapter number 6 we said that the total work should equal to the change in kinetic energy. And if the total work here is the work done by the spring, which should equal to the change in kinetic energy. And you know that the work done by the spring, it's also minus delta U. So you can say that delta K should equal to minus delta U. So K2 minus K1, it's equal to minus U2 minus U1. And that, of course, will give you K2 plus U2 will equal to K1 plus U1. We define that as E2, and we define this as E1 as we did in the last lecture, and we call this the total mechanical energy. So if the total work is done by spring, where a spring is a conservative force, then the total mechanical energy of the system is conserved. And one way of checking that, you look at delta E, where it should be equal to E2 minus E1. If that's equal to 0, then your total mechanical energy is conserved. And in this case, you will have 1/2 mv1 squared plus 1/2 kx1 squared. That means this is K1 and this is U1, equals to 1/2 mv2 squared, which is K2, plus 1/2 kx squared, and this is U2. That's the case when the total work is done by what? It's done by spring. Now, we discussed that in the last lecture. What happens if the delta E not equal to 0? We said, well, we have other forces that are doing work. And we talked in the last example about two cases or two examples where we added energy done by other forces and energy taken out of the system done by friction. So you basically have here, in this case, then you have work done by other forces. So if we want to write conservation of energy in general, okay, you know that delta E here should equal to the work done by other forces, and delta E is E2 minus E1 should equal to the work done by other forces. You can take this to the other side, so you'll have E2 should equal to E1 plus work done by other forces, and that's why we have here E1 plus work done by other forces should equal to E2. In some textbooks, they may use this as E initial, and they may use this as the final energy. So the final energy comes as a result of your initial energy plus, okay, any work done by other forces. If there are no non-conservative forces, then your energy is conserved, and your initial energy and your final energy are equal. But if you have something, you have to include that. So when we talk about mechanical energy, kinetic 1 plus potential 1 plus the work done by other forces. And by the way, work done by other forces could be positive or negative. You can add in energy or you can take out energy. It should equal to K2 plus U2. And that's how you write your energy conservation in general. And if you do not have any other forces, then you just scratch that one out and you say it's equal to what? It's equal to 0. Now, you may have cases when a gravitational potential energy and elastic potential energy are present at the same time. So you have a case here, a little girl and a dog jumping on something that has elasticity, so it has springs. So we have, when you talk about this, you'll basically have both, and we'll deal with examples where we deal with the presence of both gravitational and potential energy. So that's the more general equation here. When you write your equations, so you can say that E initial in some textbooks plus work done by, we can put other here, should equal to final energy. Is this clear? Any question on this? Is this clear? Any question on this? Now, the question that we can ask, what are these other forces? We already dealt with conservative forces, and we said conservative forces are the type of forces that conserve our energy. So they make the total mechanical energy conserved. That doesn't mean the kinetic and the potential will stay the same, but they transform from one to the other. If the kinetic increases, the potential decreases. If the potential decreases, the kinetic is going to increase. And that's how we do this. But then there is another type, which we call non-conservative forces. And this basically disturb this balance of the total mechanical energy of an object. Now, we want to look at the difference between these two. Okay. For the case of conservative forces, we talked about gravity, and we talked about spring, which is an elastic type of force. And we said these two forces are elastic forces. Now, when it comes to work done by conservative forces, now there are a few points that we want to consider. The first one, that the work done, and you see here we have CON, that means conservative, should equal to minus delta U. That's the first point. The second point, it's reversible. And the third point is independent of the path between the 2 points. It only depends on the initial position and final position. When we talked about the work done by gravity, we said it's equal to mg y1 minus mg y2. And when we talked about the work done by spring, we said it's equal to 1/2 k x1 squared minus 1/2 k x2 squared. So they only depend on the initial and final position. Now, in this case, if you take this path, the green one, or if there is something in your way, like a valley, like a mountain, and you go up, the blue one here, and you come down, and you calculate the work done by gravity, it will be the same as the one that you obtain from the green because of the initial and final position. The same thing if there is valleys in your way and you go down and then you go up, which is the red path here, it only depends on the initial and final position. And that's why we say here that it's independent of the path taken between 2 points. And 0 if the starting and ending points are the same. And it's very clear here. If y1 and y2 is equal to the same, you'll get 0. If x1 and x2 here are the same, then you will get what? You will get 0. These are properties of a conservative force. Now, a force such as a friction, this basically is a non-conservative force, because friction makes you lose energy, and the longer the path, the more energy you lose. It does not depend on initial and final position. Now, sometimes this is called dissipative forces. They take energy away from you. So these type of forces, we call them non-conservative forces. When the force does not conserve our energy, it makes us lose some energy. We'll talk later a little bit where this energy go when we lose it, or we call them dissipative forces. So we talked about that delta E should equal the work done by other forces. And delta E here means E2 minus E1, which is basically K2 plus U2 minus K1 plus U1. So you will get K2 minus K1 plus U2 minus U1. That will be delta K, and this will be delta U, and that should be equal the work done by other forces. Now, the work done by other forces, where does it go? Where do we lose it? And we will say that this actually it changes the internal energy of the system. So, for example, you have an object here, a block, moving on a surface. Now, this energy that we talk about, we're talking about the energy of the block here. This is when we talk about delta E equals E2 minus E1. If it's equal to 0, that means the energy of the block is conserved. If it's not equal to 0, that means there is friction, and that friction has taken away some energy from the block, and that's why it's reduced. But this energy that has been taken from the block, it actually goes into this surface. Okay. And this is where we say it is the system now. So this energy may go into changing the internal energy of the system. And since here we're using delta K, and since we're using delta U, in order to make the energy, this difference is equal to 0 at the end. That's why we added here delta U internal, where this should equal to minus the work done by the other forces. So we say here that work, and none here, that means non-conservative forces, which is equivalent to others. And that should equal to minus what? Minus delta U, and int here means internal. And usually it goes at what? It goes as heat. So that's usually, we say the energy is there, but it just went from one form to the other. So we say here the law of conservation of energy means that the energy is never created or destroyed, it only changes form. So when you're talking about the object like the block here, it has kinetic plus potential. It may lose energy due to friction, but that energy basically goes into the system as an internal energy, as heat. So it's not really actually, it is there. Okay? And that's why we have this law of conservation of energy. So when we have a mechanical system where we have potential plus kinetic, we look if there is any friction draining energy out, okay, and we have to consider that. Are these points clear? Are these points clear? Now, today we looked at a case when we calculated the work done by a varying force, and we defined potential energy. Is there any relation between this force and the potential energy? since we defined a potential energy, but we did that based on the work done by this force. Now, you know that we said that delta U should equal to the change, or minus the work done by the you know that when we said that the work done by a conservative force should equal to minus delta U. So delta U will equal to minus W. That's what we have here. And F here means conservative force. Now, if you take that in the limit when you make it infinitesimal, so du will equal to minus dw. And du, now when we look at dw, w, which is the work, is always the F dot R. So dw will equal to F dot dr. Now, F has an X component, Y component, and Z component. R also has an X component, Y component, and Z component. So basically, you can say that it's Fx I hat plus Fy j hat plus Fz k hat dotted with. Now, it will be dx I hat plus dy j hat plus dz k hat. If you take the dot product, it will give you fx dx, fy dy, fz dz. You're adding them. But if you have it in one dimension here, so you will have du will equal to minus fx dx if you are moving along the x-axis, like the case of a spring, for example. So now the fx here will equal to minus du by dx. So that's what we have here. Fx, it's equal to minus du by dx. And that's the relation now between the varying force and the potential energy. Now, if we look at the potential energy of a spring, where we said it's equal to 1/2 kx squared, and this is y and this is x, and you get this parabola here. Now, if I want to get my force is equal to minus du by dx. So basically, if you take du by dx, which is basically you're taking of d by dx of 1/2 kx squared. Now, x squared will give you 2x, so you'll get here kx. But since you have a minus, then the fx will du by d minus du by dx, and you get minus kx here. And minus kx is a linear relation with a negative slope. And that's how fx as a function of x here. Now, if x is less than 0 on this side here, your potential is positive. If your x is positive here, your potential is positive. But look at your force here. If x is less than 0, your force is greater than 0. And if your x is greater than 0, your force is less than 0, because of this relation here. Now, we can do that for gravity as well. Now, for gravity, you know that your potential energy is equal to mgy. And this is the potential energy, that's the y, so you'll go from negative to positive depending on y. Now, what is the force? You know that in this case, you're taking d by dy of mgy, and that will give you mg. But the F will equal to minus du by dy, which will equal to minus mg. And that's what you have here. So your Fy is equal to minus g for all values of y. Later, we'll basically talk about if the force of gravity is really constant. It's constant near heights closer to the surface of the Earth, but it may vary. Okay. So that's basically how we relate the force to the potential kinetic energy and the conservation of total mechanical energy. Any questions so far? So these are the concepts for today. What we're going to do next is basically we're going to deal with some examples. And the first example that we have here, a glider with mass sits on a frictionless horizontal air track connected to a spring with force constant K equal to 5 Newton per meter. You pull on the glider, stretching the spring 0.1 meters, which is about 10 centimeters, and releasing from rest. The glider moves back because the spring now is going to do work to its equilibrium, x is equal to 0. What is its velocity when x is equal to 0.08 meters, which is about 8 centimeters? So you're stretching the spring to this location here, where x is equal to 0.1 meters, and you release. Now, when you release, your initial velocity, or v1x, will equal to 0. Now, they ask you, what will be the v2x when your x is equal to 0.08 meters or 8 centimeters? Now, you know the only force that doing work here is the spring, and you do not have a friction. So your total mechanical energy is conserved, meaning E1 should equal to E2. So you can always compare any 2 points. So we're going to compare this point here to this point here. And we'll figure out what will be the speed when the block gets to x equal to 0.08. Our spring constant is 5 newtons per meter. Our initial x1 is equal to 0.1 meters, which is 10 centimeters. And we're starting from rest, so v1 is equal to 0. Now, x2 is when it's equal to 0.08 meters. v2 is what we want to find. And of course, there is no friction. So we have conservation of energy where E2 is equal to E1. That means kinetic 2 plus potential 2 should equal to kinetic 1 plus potential 1. So 1/2 mv2 squared plus 1/2 kx2 squared should equal to 1/2 mv1 squared plus 1/2 kx1 squared. Now, you can cancel the half out. The v1 is 0, so that basically eliminated. So out of this equation here, you can divide by m. So on this side, you will get v2 squared, and here you'll have 1 over m multiplied by k x1 squared, and you can take this to the other side here. It will give you minus kx2 squared. So the v2 squared will equal to 1 over m times kx1 squared minus kx2 squared. You can take the k as a common factor. And if you want to get the v2, you'll take the positive square root. So v2 will square root of k over m x1 squared minus x2 squared. K is 5. The mass is 0.2 kilograms. And the x is 0.1, x1, and x2 is 0.08. This v2 is equal to 0.3 meters per second. This is basically, and you can see here that the energy stays the same, but it's only the kinetic and potential that will basically change from one form to the other. This is a direct application of conservation of total mechanical energy when work is done by spring. Is this clear? Any question on this example here? Any question here? All right. Let's take an example where both the gravitational and elastic are involved. In this example here, we will look at a 2000 elevator, a 2000 kilogram elevator in a test is falling from height h 1 meter. The elevator stopped by compressing a spring 20 centimeters before it stops. So it will stop when it compresses the spring by 20 centimeters. What is the necessary force constant K for the spring? So you're coming from a height of 1 meter and you compress the spring for 20 centimeters. Now we see only gravitational forces doing work here, and we see a spring. We don't see any other forces. So we have conservation of energy here. So E2 and E1 are conserved. E1 is basically when the elevator comes from here, and E2 when the elevator basically comes here. But you have to keep, when you start from here, V1 is equal to 0, and when you come here, V2 is also equal to 0 because you stop. Moment it stops there, the spring, you're reaching the maximum compression of the spring in there. So you're going to say that K2 plus U2 due to the gravitational potential plus the elastic potential as well should equal to K1 plus U1 gravitational plus U1 elastic. Now you know that for K2 the V2 is going to equal to 0, so that goes to 0. Now you can choose your Y2 here as equal to 0. So your potential here will go to 0, the gravitational potential energy, which means that Y1 now here will equal to 1.2, will equal the difference, which is 1 meter, plus the compression, which is 0.2. So the Y1 will equal to 1.2 meters. But for the spring, you'll still have to use the X. So the first X is 0, and the compression is 0.2 meters, which is 20 centimeters. It translates into 0.2 meters. So now when you do that, your K2 is gone. Your potential, gravitational potential energy is 0 because you set that Y2 is equal to 0. Your elastic potential energy 2, it's equal to 1/2 kx2 squared because it's compressed. Now K1 is 0 because it's starting from rest. Your gravitational potential energy 1, it's equal to mgy1, and y1 is equal to 1.2 meters. Your elastic potential energy, it's equal to 0 because the spring when you start is not compressed, so that goes to 0. So the only thing that you have here, you have 1/2 kx2 squared equals to mgy, and your interest is in k. So you can basically multiply this by 2 to get rid of the half, so you multiply and you divide by x squared. So the k here will equal to mgy1 over x2 squared. So it is 2 times 2000 times 9.8 times 1.2 divided by 0.2 squared, and the k here comes as 11.76 times 10 to the 5 in Newton per meter. And this is now how we obtain the spring constant K from a situation like this. This situation here, only conservative forces are doing work, gravitational and elastic. And you just use conservation of energy and What they ask us is to find k, and that's how we did it. Is this clear? Any question on this one? Any question on this one? Let's take another example here. Maybe you have to think a bit here. You are rearranging your furniture and you wish to move a 40 kilogram photon 2.5 meters across the room. So you're going from point 1 to point 2. The distance from here to here is 2.5 meters. A heavy coffee table, which you don't want to move, blocks this straight line path. Instead, you don't want to move this table here. You slide the photon along a dog-leg path. The dog legs are 2 meters, 1.5 meters, but there is a friction, and the coefficient of kinetic friction between the photon and the floor is 0.2. Now they ask you how much work must you do to push the photon along the dogleg path, then along the straight line path. So if the coffee table is not here and you go this way, how much work should you do? But now you're going along this way, how much work you do? And probably you will do more work. We want to know the difference. So we want to look at path 1. We're going straight, which is in this case, it's 2.5 meters. And this one is 2 meters. And this one here is 1.5 meters. Now we want to look at the difference in work between going this way, which is 2 meters than 1.5, and we assume that's going to be bigger, and going straight that way, but we did not do that because of what? Because of the photon that it will be in our way. Now, the total work here should equal to 0. You can argue about that. You know that we said that the total work should equal to the change in kinetic energy. Now you're starting from rest, where it should be 1/2 m v1 squared, v2 squared minus 1/2 m v2 squared. So you're starting from rest and you're stopping. So you know that the total work is going to equal to 0. But this total work will come from 2 things. Will come from the work that you do, which we call applied work, and the work done by friction, and that should equal to 0. So the work done by the applied force should equal minus the work done by friction. So if we take the second case, then we'll say the work done by the applied force along path 2 should equal minus the work done by friction along this one. You know that when you talk about work, you say it is F dot S, which is equal to Fs cosine phi. In this case, friction, you will say that's equal to Fk S cosine 180 degrees. And you know that the force of kinetic friction is equal to the mu k times the normal force times S times cosine 180 degrees. And the normal force in this case should equal to mg. So your normal force here will equal to mg. So when you look at the work done by friction, which we say here, it's minus the work that we do along path 2 should equal minus the work done by friction, which is equal to minus Fks cosine 180 degrees. Cosine 180 degrees gives you minus 1. And the normal force here should equal to mg, which is 40 times 9.8. And we'll do that. We can do it 2 and then 1 1.5. So we're just adding both of them. You will get the result. You can do this way and that way, but you can add them up. So it's 3.5. Minus times minus will give you 1. And this gives you 274.7 joules. That's the work that you do against friction to go on path 2. If you do that along 1, and that's why we say 1 here, 1 here, minus mu k ns cosine 180 degrees. Cosine 180 degrees will give you minus 1, and you have minus 1 here, it will be plus. The mu k is equal to 0.2, the n is equal 40 times 9.8, the s is equal to 2.5. That's path 1 here. And you get 196.2 joules. So the difference in work between the two paths will be 274.7 minus 196.2 and gives you 78.5 joules. So that's how much extra work you have to do in order to bypass moving the heavy coffee table. Is this example clear? Any question on this one? Any question? We're just trying to apply what we learned from conservation of total mechanical energy. Let's deal with another example, and we've seen this before, but it's different now. A boy skateboards from rest down a curved ramp with a friction, so there is a friction. If the heat the boy and his skates as, if we treat the boy and his skateboard as a particle having a total mass of 25 kilogram, he moves through a quarter circle of radius r, 3 meters. The boy's speed at the bottom is 6 meters per second. What work was done on him by the friction force? And then what is the change of the system's internal energy? So the boy starts from here, from this point here. From rest, V initial is equal to 0, or V1 is equal to 0. Now the height, Y1 will equal to 3 here, and Y2 here will take it as 0. But when he gets to this point here, the V2 is equal to 6 meters per second. So the mass is 25, Y1 is 3, Y2 is 0, V2 is 6 meters per second, and V1 is 0, starting from rest. Now, they tell us that there is a friction. And I know that I will have a delta E. E2 minus E1 is not going to equal to 0, but it will equal to work done by other forces. And that work is done by friction. So the work done by friction here will equal to E2, which is K2 minus U2. And I only have a gravity here. That's I only have a gravitational potential energy here, minus E1 is K1 plus U1. But K1 is equal to 0 because you're starting V1 is equal to 0. And your potential 2 is equal to 0 because you set your Y2 is equal to 0. So the work done by friction will equal to 1/2 mv2 squared minus mgy1, which is 1/2 times 25 times 6 squared minus 25 times 9.8 times 3, and this gives you 450 minus 735, and the work done by friction minus 285 joules, and we expect that to be minus because it's taken out of the total energy, mechanical energy of the boy. Now, where did this energy go? And that's when we say, what is the change in the system's internal energy. Now, we're not just talking about the object, the boy. We're talking about the whole system now. And this is where the energy has gone. And that's what we said when we said delta U internal, which the change in the internal energy of the system should equal minus the work done by other forces. And in this case, the work done by other forces, it is the work done by friction. So you have minus here, and the work done by friction is minus 285 joules. So the change in the internal energy of the system is 285 joules. Is this clear? Any question on this? Any question on this? So we did, if we just quickly try to look at what we did in the previous slides, we said that the work done by spring should equal to 1/2 k x1 squared minus 1/2 k x2 squared. I told you in some textbooks they may say initial and final. We define elastic potential energy as 1/2 k x squared. So in this we said that the work done by the spring, it should equal to minus delta U. And in that case, if the total work is done by the work of the spring, then we have E2 is equal to E1, and we have conservation of total mechanical energy. But in cases we have a delta E, then this should equal to the work done by other forces, and we said that E1 plus work done by other forces should equal to E2, where this work done, which in some cases could be friction and it takes energy away from you, we said, well, delta U internal should equal minus the work done by the other forces, and this is where it goes into the changing the internal energy of the system, not just the object. Now, let's take a few questions here just to probably test our understanding. You have a block is released from rest on a frictionless incline as shown when the moving block is in contact with the spring and compressing it. What is happening to the gravitational potential energy, U grav, and the elastic potential energy, UL? Well, you know that you're starting Y here, and probably you'll get to some Y2. You know that Y1 is greater than Y2, and gravitational potential energy is defined as mg Y. So what happens here? We say that the gravitational potential energy is going to decrease. But when the block basically presses on the spring, it will compress the spring. And in that case, the elastic potential energy is going to increase. And that's why the answer here is D. In this question here, you have potential as a function of x. The graph shows the potential energy for a particle that moves along the x-axis. The particle initially at x is equal to d moves in the negative x direction. That doesn't mean that x is negative, but it's moving in that direction. That means it's moving this way. At which of the labeled x coordinates is the particles slowing down? Now, you know that what you have here, you have a conservative forces, so your energy is conserved, potential plus kinetic. So at any point, if the potential increases, the kinetic decreases. If the potential decreases, the kinetic is going to increase. Now they ask us slowing down. Slowing down, that means the speed is lower, which means lower kinetic energy. So I look for situation when the kinetic energy is decreasing. meaning that the potential energy is going to be increasing. So here, point A here, it shows me that the potential energy is increasing. And if the potential energy is increasing, then the kinetic energy is decreasing. And if the kinetic energy is decreasing, that means you're slowing down. So the right answer here is A. Is this clear? Any question on this? We'll deal with the same question again, but the question here, we want to relate force to potential energy. At which of the labeled x coordinates is there zero force on the particle? We already said that Fx should equal to minus du by dx. So if you want to do that from the graph, you're just basically taking slopes. And you want this to equal to 0, right? So actually at point D, the slope here is equal to 0. And at point B here, the slope is equal to 0. So that's basically when the force is going to equal to what? It's going to equal to 0. That's basically where we're going to relate the force to the potential energy. Is this clear? Any questions on this? All right. I want to bring to your attention something that probably you can ask. Okay. We assume that gravity is a constant force, but that only happens near the surface of the Earth. If you recall, in chapter number 5, I told you about the Newton's law of universal gravitation, and we said usually F is equal to G m1 m2 over r squared, but r is measured from the center to the center. So I told you for an object on the surface of the Earth, basically the r will equal to the radius of the Earth and mass of the Earth, and we calculated the G, and we said the G is almost equal to 9.8 meters per second squared. So I told you near the surface of the Earth, or if you go a little bit further, it's not going to make any difference because the radius of the Earth is, roughly speaking, 6.38 times 10 to the 6 meters. So that's not going to change a lot. And that's why we picked G more or less to be constant. And that's why we looked at the force of gravity here to be constant. But if you go higher and higher from the surface of the Earth, then your R, which will be RE plus H, whatever you're going higher there, that will basically change your force. So it's not going to be a constant force. So if we go back to what we did in today's lecture, when we said that we want to calculate the work done by a varying force, and we said it should be the integral of F dot dr. But now, if you have an object, this is, let's say, the Earth, and an object far away here, let's say a satellite, whatever it is, well, you always measure from the center. So this is RE, and of course you add H here. So let's call this R, where R should equal to RE plus H, but we'll use R for it. But we said that F should equal to G m of the Earth, mass of the object that you have, divided by R squared. R could be RE plus H, but we're just going to put it as R here. So if you want to calculate the work now, it should be G, the integral of G m of the Earth, mass of the object, over r squared dr. But now, remember, we set y equal to 0 at the surface of the Earth. That's when we talked about the gravitational potential energy. And we said that the UG should equal to mgy. And as you go higher, okay, you will basically getting more and more potential energy. But as I told you, this gravitational force, it depends on the radius. So it's a varying force. So for objects that are far from the Earth, we have to do it this way. But now, where are we going to set our reference of potential energy equal to 0? Well, when you are further away from the Earth, that's when you have no effect, and that will be the 0. So usually you will say that you will go from R1 to R2, or R initial to R final, but I'm going to set this one at infinity, because this is where it's going to be 0. And if I want to do it at the surface of the Earth, then this one I will set it as RE. So the integral here will be from infinity to RE, G m Earth mass 1 over r squared delta r. This is a constant. I can take it outside the integral. But I have to integrate 1 over r squared. Now, just to remind you of what you did in calculus, if you take d by dx of x raised to the power n, you say this will equal to n x n minus 1. And if you want to integrate x to the n dx, you always say that that should equal to 1 over n plus 1 x n plus 1. So the case of when you have the integral of 1 over r squared delta r. Well, r squared, 1 over r squared, it's like saying that it's the integral of r minus 2 dr. So now, if you want to integrate that, you will say it is equal to 1 over minus 2 plus 1 raised to the power r minus 2 plus 1. And that, of course, will give you 1 over minus 1 r to the minus 1. And that basically will give you 1 over r, because r raised to the power minus 1 is 1 over r. So this integral of 1 over r squared over that will give you minus 1 over r. So what you will get from here, you will get minus g m e m over r, and you will integrate that from infinity to r, okay, or re, for example, here. But you can keep it r in general. Okay. But this will give you 0 here. So this will give you minus g m over re in this case, minus g m e m over infinity, okay, and that of course will be 0. So this is what you're going to get now. So your work, which is done, okay, by gravity, now when you look at the potential is going to equal to minus a g m over r, or in the surface it will be re. So you have to be careful. Okay. Now, when we're dealing with things near the surface of the Earth or at moderate heights, it's okay to consider gravity to be constant. But if you're going higher and higher, well, that's when you actually have to treat it as a varying force, because it will go as a function of 1 over r squared. I'm talking about the force. Of course, the potential will go as 1 over r, or minus 1 over r. Now, this brings in an interesting point about something that we call escape velocity. So you have, let's say, it could be any planet, it could be the sun, but let's say it's the Earth here, and you want to throw something up. If you throw it, it will come back because of gravity. But we want to escape the Earth. That means it will leave the Earth. So what will be the minimum speed? And sometimes it's called escape velocity, at which you're going to throw the object and it will leave the Earth. So the way that you're going to do that, you go from here. So if an object is located here, so we're going to look at E1 here and E2 there. And since only gravities don't work here, so we can say that E1 should equal to E2. But E1 will equal to K1 plus U1, and that should equal to K2 plus U2. Now, your K1 will equal to 1/2 mv1 squared. But your potential one now, it's going to equal to minus g mass of the Earth. By the way, you can do it for any planet and you keep the mass of the object over the radius of the Earth. That's what we did in the previous slide. Now, K2 will equal to 1/2 mv2 squared plus minus, because the minus g m of the Earth, mass of the object over r2 here. Okay. Now we want the object to escape. Okay. So it should be far away from the Earth. Okay. So that should be gone. Okay. And you know, when you go higher, your kinetic energy is going to decrease in favor of potential energy. But here, I just want to give it the minimum energy that it reaches that. So actually, I don't want it to have kinetic there as well. Okay, it is the minimum energy that it gives that it escapes from the Earth. So that's also equal to, sorry, here, this one is equal to infinity. So that goes to 0 here. So you have this equal to 0. So 1/2 mv1 squared minus g m the Earth of it's equal r is equal to 0. That means 1/2 mv1 squared should equal to g mass of the Earth, mass of the object over the radius of the Earth here. And this is basically the minimum speed that you give to escape from the Earth. So you can cancel here the mass. You can cancel the half and multiply here by 2. So your v now, and let's call this e here, meaning escape speed, it will be the square root of 2g mass of the Earth over the radius of the Earth. If you do the calculation here using, it will roughly give you about 11.2 kilometers per second. And this is basically the escape velocity, or the escape speed, the minimum that if you leave the Earth, you're not going to come back. The Earth cannot basically bring you back. Of course, satellites fall in orbit. They're affected by the gravity of the Earth. But I'm saying it will leave the Earth. That's it. And this is the minimum escape velocity that you need to do that. Now, just to bring another thing, and you may hear this also about something that called orbital velocity. And orbital velocity comes that if you have two objects, the force between them, it will be g, m of the Earth, m of the object over, 1/2 mv1 squared, 1/2 mv2 squared, plus g m of the Earth, m of the object over the radius of the Earth. And this is basically the minimum speed that you give to escape from the Earth. So you can cancel here the the radius of the Earth plus how far is the object squared, and that should equal to mv squared divided by re plus h. You can cancel the m from both sides, and you can cancel this with that. Okay, so your v will be the square root of a g mass of the Earth divided by re plus h, and this is sometimes is referred to as orbital velocity. Okay, not the escape velocity, just to, and this is what you can calculate for satellites and so on, just to, and that's roughly speaking. Okay, uh, um, you can also calculate a value for this. Okay, depending on how far you are and things like that. Okay, so just to bring this point in, but here you can use energy concept to calculate your escape velocity. Now, if you're fortunate and you take other forces, other courses in physics, and you will be dealing with describing orbits and so on, you're not going to use forces, but you're going to use the concept of energy. You may things like Lagrangian and Hamiltonians and so on. I just wanted to bring this point in, probably on escape speed and also gravity, why we consider it constant, but in reality, if you go further and further, it should not be looked at it this way. Any questions so far? So, to summarize the highlights of our lecture today, we talked about elastic potential energy, which is equal to 1/2 kx squared. Now, we said we can look at total potential energy where it can have a gravitational and elastic potential. We did example on the elevator. We said that E1 plus work done by other forces should equal to E2. So where do this energy go? Actually, it goes in changing the internal energy of the system, not the object. And that's why we say that delta U in turn will equal to minus the work done by non-conservative forces. Finally, if delta K plus delta U equal to 0, that means your energy is conserved. But if it's not equal to 0, then you have work done by other forces. And we equated that to the change in the internal energy of the system. And that's why we said the energy is not created or destroyed, but it transforms one form to the other. And finally, we related the varying force to the potential as F is equal minus du by dx. If y is equal to minus du by dy, you can also do that if z equal to minus du by dz. Is this clear? Any questions on these? Good.